Hello, and a very warm welcome to this talk about the kind of super radar a mathematician might imagine. In our case, Henri Poincaré, the 19th century French mathematician and philosopher of science, whose eponymous sphere is still used for a description of polarized waves. We will use it and them to explore a new way to process radar images, now available from an ever-increasing constellation of satellites in low Earth orbit. My name is Shane Cloud, until recently director of AEL Consultants, working for over 20 years in R&D and training for those interested in polarization in radar and optics. This talk is actually a revisitation of some work carried out long before that I contributed to nearly 40 years ago as a young PhD student. At the time, the potential of polarization in radar was seen as exploiting orthogonality, the ability to switch things on and off, in radar terms, removing the clutter, a switch, 1 or 0, at our control. At the time, I started to think how to apply orthogonality to full Muller matrix polarimetry, but was deflected, as many were, by an insistence on prioritizing the multi-channel information potential of radar, rather than wasting channels using orthogonality. You see, in a sense, orthogonality means you have to measure something to get nothing, and project managers, then and now, don't like statements like that. I wish I had stuck with it more, of course, had the courage of my own convictions. An important side note to present PhD students, stick with it if you believe it. But I'm pleased today to revisit these early ideas with a modern twist. So, I present this not in any sense of regret, just like the words of the famous French song, nor am I looking back in anger, but I'm pleased to now see this work in its broader context, and how I hope to show you it opens new possibilities and options for the processing of future satellite radar data. I'm going to describe some history, develop some new theory, then show you application to some real data, and for that I acknowledge the support of the European and Japanese space agencies ESA and JAXA. So, time to design a radar that Poincaré would be truly proud of, Poincaré's radar. So let's go see just how to do it. The idea of bouncing radio waves off space objects started with a simple concept, if not a massive piece of engineering. Just look at the scale of this Satelloon, a satellite balloon called ECHO, built by a fledgling NASA in 1961. Put a giant sphere in space and point an antenna at it to reflect waves back down to Earth. Now more often we reverse that idea and put an antenna in space to look at an even larger sphere, the Earth itself, Earth observation, or EO. The subject has surely advanced beyond recognition since 1961, a technology that now sees dozens of high-resolution imaging radars in orbit around the Earth, providing a basic currency for exciting new developments in data sciences around the world. But a sphere's geometry would be all too familiar to Poincaré. So let's go see a modern example of a new space radar that would intrigue him very much more. Meet ESA's new satellite radar, Biomass, to be launched 2023, and involving, in the spirit of ECHO, deployment of a very large reflector antenna in space to allow imaging at long wavelengths around 70 centimeters. Its mission objective is to measure forest biomass globally and repeatably. But its technology requires measurement of the full 2x2 polarization scattering matrix for each pixel on the Earth. We shall see how challenging this is in a moment. Such missions, of course, are expensive and only come after years of study, and this one can be seen as a direct consequence of the multi-channel information content approach started way back in the 1990s and alluded to in my intro. But time now to redress the balance and show how orthogonality can play a role for such sensors. And Poincaré has a lot to tell us about orthogonality. Let's start by considering old ortho, some background ideas and historical developments that help pave the way to the new ortho we shall develop later. So first, some background context, especially for those not familiar with the idea of what we mean by orthogonality and especially its geometry on the Poincaré sphere. We will get to the mathematical definition soon, but first a bit of geometry, starting with the polarization ellipse itself. Polarized waves come in many shapes and forms. Linear polarizations are intuitively the easiest to visualize. Light oscillating up and down in a particular spatial direction, maybe horizontal, h, or vertical, v, here shown at 45 degrees. But transverse EM waves can have circular polarization, where the electric field traces out a helix in space, appearing as circular motion in a plane. In general, this circle can become an ellipse. Now, all possible such states can be nicely mapped onto the surface of a sphere, called the Poincaré sphere, as shown lower right, with circular at the poles, and all linear states around the equator. Key for us is that for each such blue state, there is a unique partner, the red states. These are the orthogonal partners. In the linear case, we can see a direct link to spatial orthogonality, but less obvious is the idea that circular has an ortho partner, a circle with the opposite sense, orthogonality encoded in time, going around clockwise or anti-clockwise. All elliptical states on the sphere have an ortho partner, and this ortho condition has a simple geometrical property on the sphere. For any given point P, the orthogonal state lies on the antipodal point, on the end of a diameter passing through the center. For example, if we sit at the North Pole with circular pole, then its ortho partner is at the South Pole. So, two things to remember. Every state has an ortho partner, and that partner is unique. Let's look at a bit of the algebra for describing these orthostates. First, how to describe a state of polarization. And let's use a bit of geometry to help clarify the options for the algebra. Consider a general elliptical state, P, on the Poincaré sphere as shown. Now we can reach P either by giving its Cartesian coordinates, x, y, z, which are just the Stokes parameters, or we can locate P using the geometry of its ellipse, its major axis orientation angle theta, and ellipticity or fatness of the ellipse, tau. These are then just the longitude and latitude of a point on the surface of the sphere, the blue way. However, there is a third option. We can form a spherical triangle by tilting a plane by an angle delta and moving along a great circle by another angle 2 alpha. Let's call it the green way. This green way, in fact, is related to ratios of the electric field components, the usual preference in radar studies, where it is most commonly used. Also, and key for us, it can be generalized to high-dimensional algebraic forms, as we will show. So let's put all these ideas together and formalize what we mean by orthogonality. So here we are. We start by specifying a general state P, either as a two-component complex vector E1 or a real Stokes vector G1, using the ellipse geometry theta and tau. Note how the alpha angle arises from the amplitude ratio of components of E, while the tilt of the plane delta is just a phase difference between components. Then we have some simple algebraic operations to find the ortho partner E2 or G2, which is unique. For example, for the Stokes vector, we just negate the x, y, and z components. The key result, defining orthogonality, is then forming the appropriate inner product of two somethings to get nothing. An appealing idea, but one complicated by the fact that radar does not control its reflected wave. It comes back somehow transformed by an unknown scattering process. So how can we possibly control these orthostates in practice? Well, geometry helps yet again. Just remember in what follows that the orthogonal state is found by reflecting P on the sphere through the origin to the antipodal point, a reflection operation, and we will see that reflection operations are key to us understanding this transformation by a scatterer. This transformation of the radar signal is controlled by four complex numbers, elements of the 2x2 complex scattering amplitude matrix S, which relates incident and reflected waves. In backscatter, in radar antenna coordinates, this matrix is symmetric due to the reciprocity theorem. And symmetric, complex 2x2 matrices have a nice geometry on the Poincaré sphere. All controlled not by reflection of a point P through the sphere origin, but reflection through a shifted fixed point I, defined formally from the ratio of singular values of S. followed by a 180-degree rotation about an axis defined by the phase difference between singular values. So a general scatterer acts to shoot a ray through some offset point, then rotate it by pi. Simple geometry, actually, to understand so many complicated possible scattering events, and this pattern leads to a few surprising results and a way to control orthogonality, as we now show. So let's start top left. Here we have a diameter on the sphere in red, defined by two orthogonal states, which are the singular vectors of S. So this represents a scattering mechanism. Along this axis is our point somewhere. Let's mark it as I. Now consider some choice for the transmitter state P that we've made. This is in the second sphere. We see the point P. Reflect it through I, then in the next sphere rotate it by pi. And we see the return state is not generally orthogonal to the transmit. So P, in a sense, was a bad choice. We haven't managed to achieve orthogonality. But we can see from the geometry that if we choose P sitting directly above I on the sphere, as shown lower left, then voila, the return signal is guaranteed to be orthogonal. And in fact there are two such states by symmetry above and below the point I. This was early ortho in radar terms and led to a key development, the idea of adaptively changing the antenna polarization by measuring S in real time to track these nulls, the null condition. It was called VPA, or virtual polarization adaptation. But it meant we had to measure the full S matrix in real time. That was the big initiative. And how difficult can that be with a radar? Let's have a look. Please allow me an indulgence. One man took this idea that the future of radar was to measure S all the time and everywhere to great lengths. He would tell anybody who would listen, and many who wouldn't, bursting into offices uninvited, just what to do. Wolfgang Berner was an inspiration for many young PhDs in radar, me included, and never gave up on his message. For that reason, allow me to call a radar that measures S for each pixel a Berner machine. Just to be clear, nobody else uses that term, but I hope it will become clear as we go the respect he deserves, given all the problems to be overcome, and they were, one by one. Let's see what kind of problems arise. So the first thing is, how do we form an image? Well, radars are a form of clock system. They measure time between a transmit pulse and its return, so enabling separation of objects in range, or one direction. Light travels almost exactly 1 foot in 1 nanosecond. A reason perhaps to return to imperial units? Anyway, and so the timings required depend on how far away an object is. However, the range resolution always depends on how narrow the pulse is, or more usually these days its bandwidth B, as chirp waveforms are pretty ubiquitous now rather than short pulses. But this is still a one-dimensional image, really, not really what we would describe as a useful image. And the point here is, how do we separate objects at the same range, schematically shown here like pixel Q? How do we separate all those in the cross range or azimuth direction? The answer is to do something to break the symmetry of points along a constant range line. To illustrate, imagine trying to separate left and right from a transmitting source. The answer is to move in a particular direction. When you move, here for example objects to the left will have a lower frequency, a so-called redshift, and to the right a slightly higher frequency, a blue shift, both due to the Doppler effect. To do this for radar we need to move orthogonal to the range direction, called the azimuth direction because of its relation to antenna patterns. Then we measure the Doppler shift as a function of time. When it is 0, we have found the point Q. And an amazing result. The resolution we can achieve gets better with smaller antennas. In fact, it is just d over t2, where d is the real aperture of the antenna. Why? Well, because smaller antennas see more of a Doppler history in time because of their wider beams. So the size of a pixel in our final image depends on two parameters, the transmitting bandwidth B and the real antenna aperture D. So now we have a match made in the heavens. Stick a radar on a satellite, which can't stop falling, with an antenna pointing at right angles to the flight direction, and we have a 2D imaging system. So here is an example geometry. The very first commercial imaging radar in space was CSAT in 1978. It only lasted 100 days, but started a revolution by showing what was possible. Now there are dozens in orbit, and many commercial companies drive constellations of them. But here we have just an example parameter set for a typical low Earth orbit. This is ERS, which was an ESA satellite from the 1990s. Moving along at about 7.5 kilometers per second in orbit with a wavelength of 6 centimeters and a typical antenna dimensions, generates Doppler shifts in the kilohertz range. But as radars are pulsed systems, we need to make sure that the pulse repetition frequency, the PRF, is high enough to sample the highest Doppler shifts without aliasing. And if the antenna gets smaller, we get higher Doppler shifts, so we need a higher PRF required. So resolution is intimately linked to how many pulses per second we send out. One of the many compromises required in radar imaging. So, on to design our burner machine. So how do we measure S for each pixel in an image? Well, we need two ideas. First, we need to switch the polarization of the transmitter pulse to pulse between any two ortho states we see here, 1, 0, the blue one to start with. The next pulse is 0, 1, then 1, 0, 0, 1, etc. Now these are usually horizontal and vertical linear polarizations, but they can be any pair of orthogonal states. Then we need a coherent receiver with a equivalent of a radar beam splitter, that is, splitting the received signal into two orthogonal channels. Now this orthogonal split can be the same or different to the transmitter, but in principle it's the same idea. So it takes two pulses to measure a full matrix, column by column. Then you repeat to make two time series for Doppler analysis, right, to be able to do the cross-range imaging. So it's the red and the blue pulse streams above. And one problem immediately, we effectively halve the PRF of an equivalent single polarization radar, the distance between the blue pulses, for example. This limits our Doppler accuracy, or we can double the PRF, you might say, but this too comes with a price, as we shall see. But all seems clear. Some key enabling technology in switches and beam splitters, and initially there was a struggle there, but we got over that. Then all is well, is it not? I'm afraid not. Just the beginning of our troubles. Let's turn to Wolfgang Pauli to see more. So this innocent set of 4 2x2 matrices plays a central role in many aspects of polarization algebra. Defined simply as algebraic things that square to the identity, they have three main uses for us. They underpin, in fact, the geometry of the Poincaré sphere. They provide the connection between algebra and geometry. They expose physics in propagation and scattering matrices, as we'll see. And as we shall also see, they play an important role in understanding the darkest workings of a burner machine. Let's look at some examples. So here's the first application of the Pauli. It is simply to expand the scattering matrix, this set of 4 numbers, for each pixel using the Pauli set as basis to generate a vector. So we go from S to a set of coefficients AI, which can be stacked into a vector with 4 complex elements. This process is called vectorization. There is a familiar form of this idea in the well-known relationship between the 2x2 Hermitian wave coherency matrix C and the Stokes vector G. That's also vectorization from a matrix to a vector. But we can also do it with any 2x2 complex matrix. As we can see, it leads simply to sums and differences of complex numbers. Surely not that useful, but actually very much so. It forms the basis for the multi-channel approach to radar polarimetry via decomposition theory, especially via the covariance of this vector K that we have defined for a complex matrix S. A 4x4 Hermitian matrix called the scattering coherency matrix T, which has a key relationship and one-to-one mapping to the full Muller matrix of Stokes algebra. So T will be the kernel for all our discussions of orthogonality. Just remember, it is a proxy for M, the Muller matrix, and so contains the same information. A second key idea is that the mapping of rotations and other smooth transformations from the matrix to the vector is relatively easy using Pauli. For example, a standard rotation through theta, an orthogonal similarity transformation of S, translates to a simple double-angle plane rotation of the vector. So for example, the first Pauli element, HH plus VV, is invariant to rotations. You can also deal with stranger types of transformation, such as weird rotations that don't involve a transpose in the second manifestation of R. And these do actually arise in physical applications, particularly in Faraday rotation for satellite radio propagation through the ionosphere. And again, we see a simple sparse unitary matrix transforming the Pauli vector. This form allows simple estimation and removal of any Faraday rotation from the signal, a technique of vital importance, by the way, for the successful operation of the biomass mission. Finally, we come to the most general case, a similarity transformation of S by an arbitrary 2x2 complex matrix P. This too has a relatively simple matrix form in Pauli vector form with a row and column of zeros. So the first Pauli channel, again HH plus VV, is invariant to all such distortions, whatever the values you put into P. This case arises when considering calibration of our burner machine to account for errors in the transmitter and receiver, as follows. So the radar calibration problem can be stated as shown, that the observed matrix is a cascade of the true matrix S sandwiched between a transmitter distortion T and a receiver distortion R. Now we can exploit the ideas of Pauli vectorization by first measuring the response of our system for a mirror on the ground, usually in radar terms the form of a large corner reflector as shown here. We can then isolate R or T in two similarity transformations by finding the inverse of the measured matrix for the mirror. This then allows us to use the Pauli matrix formalism to devise an efficient algorithm for estimating R and T and removing them from the data. More details can be found in this article. So Pauli matrices help in extracting physics from the scattering and in understanding and removing unwanted transformations like Faraday rotation and receiver and transmitter distortions. They have one further use, however, in understanding image distortions in our burner machine. So a simple question, what happens to a matrix if we right multiply it with the Pauli set? So take an S, multiply it by sigma 0 in the first example. Nothing changes, of course, as sigma 0 is the identity matrix. But for the others, something happens, yielding a set of simple operations, column swaps and negations of S and combinations. And it turns out these are important in a consideration of radar image distortions. And two examples now to demonstrate. The usual literature term for our burner machine is just SAR, or PolSAR for short, polarimetric SAR. Whatever we call it, remember we measure the S matrix one column at a time. So we transmit the first H pulse and receive the first column OK. But of course that pulse doesn't stop. It continues in space, and so if we're unlucky it will return much later in time, in fact perhaps during the time we are listening for the second column. Think about it, and we see that a column swap is happening. Column 1 of the ambiguity on top of column 2 of normal, and vice versa. This is a real problem for measurement of the usually much smaller cross-pole channels HV and VH. We see that because of the column swap, they are sensitive to copolar ambiguities, which can be much larger due, for example, to specular flashes far, far out in range coming in and distorting. All this mess can be simply characterized by noting that the ambiguous matrix SR is multiplied by sigma 2, the column swap operation. This we can then use in analysis of the image distortions, just keeping it in the algebra, and it'll keep everything right. All the properties of sigma 2 will be useful in making calculations. So that's range ambiguities. Well, I'm afraid there are more. In the other direction, remember we measure Doppler. And to get cross-range imaging, we need to measure this Doppler shifts. But we are using a pulse system, so we sample. And we have to make sure that the pulse sampling is high enough to avoid aliasing of very high Doppler frequencies. But this is difficult, as real antennas have side lobes, and by definition these side lobes point to regions of very high Doppler, far out in angle. So 2 points A and B, separated in azimuth, can be superimposed and their S matrices coherently added. This happens because the very high Doppler frequency from B is aliased on top of A, appearing as a lower frequency because of our inadequate pulse sampling. So what is the relationship this time between the true desired S matrix for a pixel and its Doppler ambiguity? Remember that we measure 2 columns of S separated in space, in fact, by 1 pulse interval. So we have to co-register the 2 sequences we need to use interpolation so that both columns represent the same pixel. In doing this, we incur not a column swap, but a column negation on the ambiguous signal. This negation means that off-diagonal elements of the ambiguous signal are in fact 180 degrees out of phase, while the true matrix are in phase. And it suggests a simple algorithm. If we just add HV and VH, which is in fact one of the Pauli vectorizations, if you recall, this will cancel the ambiguity, because when we take HV plus VH, it will become 0 for the ambiguous channel. Again, we can use a Pauli matrix operator to keep account of this type of distortion, this time sigma 1. So slowly we are building a model for image formation, including transmitter-receiver distortions and now image ambiguities. So let's pull it all together. So here it is, our full model for how a Berner machine works. T is a transmitter distortion, F a rotation matrix representing one-way Faraday rotation, and R the receiver matrix. And of course we're working from space with limited power, and so additive noise N can be an issue. Although there are now several established methods for noise mitigation. You can see the reference here for an example. And so here we will ignore N just for simplicity. But even so, there is still an elephant in the room, so far not mentioned. Yes, we can obtain a calibrated S for each pixel and understand the distortions that may be present. But coherent imaging has a twist. The S matrices we get show large variance of parameters due to speckle. Time to face it now. So here is a simulation to illustrate the problem of speckle. In this simulation we have a uniform background reflectivity, but if we take just the raw output of a SAR processor called one-look imagery, we see the salt and pepper signature of speckle. These fluctuations can be severe. One way to measure them is to evaluate the coefficient of variation, CV, as the ratio of a local standard deviation over the mean. Ideally this would be close to 0, but it goes as 1 over the square root of n, and if n is equal to 1, we have a standard deviation equal to the mean. So in brighter areas of the image, the mean is high, and the standard deviation is also high. The way to fight speckle is to filter or smooth the data by taking multiple looks. Can, for example, be done by chopping up the Doppler spectrum we measured into pieces, processing each piece and adding the results. In any case, local averaging of some kind is needed, and this invariably reduces resolution. But it also poses us a problem for a Berner machine. Remember, we need an S matrix for each pixel to exploit orthogonality. But which S value do we take? So here we have a schematic of a pixel in the center there, the nth pixel, and the question is, what S matrix or equivalent Pauli vector do we take? The answer is to take some kind of weighted local sum of nearby pixels. But not their k-vectors, they are complex and they will quickly average to 0. No, we must add their weighted t matrices or covariances of the vectors. The problem, of course, is now that t is no longer of rank 1. It has no single equivalent Pauli vector. It is generally of full rank. Its corresponding Muller matrix has no single Jones matrix. It is a depolarizer, and depolarizers destroy information, don't they? Well, this is one reason why orthogonality was abandoned. People gave up at this stage, but we can take it a little bit further. First of all, the information is not destroyed entirely by depolarization. As shown first in calculations of light scattering by atmospheres by Chandrasekhar in his book on radiative transfer, some information survives the averaging, an idea that has since grown into the decomposition industry. There are lots of them now. But we're going to take a different route. Remember, orthogonality is our objective. Let's take a new look at it. First of all, ignoring speckle, let's park that elephant and wake it up later. Let's pretend we can take each calibrated pixel S matrix at face value, single look imagery to start with. It's time to think about generalizing our idea of orthogonality. So recall, if we have an S matrix for each pixel from our burner machine, then we can null that pixel by transmitting a special state of polarization. Those, remember, above or below a point I inside the Poincaré sphere. However, this state will vary from pixel to pixel as S changes, and by choosing one pixel to null, we ask, what about the others? They will of course give a non-zero response in general, but it is only a kind of one-dimensional scalar image we obtain, i.e. just the response you get by transmitting a single polarization, that special state that makes an individual pixel null. And generally it will be sub-optimum. So can we do better? Can we use an S to still null a pixel and yet somehow at the same time optimize the signals from all the other pixels? A constrained optimization problem. They, after all, might contain some differences to our reference that we are desperate to detect. A small boat on a rough ocean, or in optical terms, a cancerous tumor in a healthy tissue background, for example. To answer this, we need to consider new ortho, or multidimensional orthogonality, as follows. For wave states on the Poincaré sphere, there is a unique ortho partner, as we discussed earlier, and as shown again across the top line here, with E1 and E2 being the two orthogonal states. But now we have a Pauli vector, K for each pixel, not a wave, but a higher dimensional complex vector, and we really should use all of it, if possible, in the process. So first we take a reference K vector, as shown. We can first normalize it to isolate a unitary vector, E1, as shown. Note that we use alpha S for this vector to differentiate it from the wave alpha used above for the wave itself. Now, for an n-dimensional vector, we have n-1 vectors in the orthogonal space. And here is an example. If we define E1 as our reference, then E2 and E3 span a 2D space of possible orthopartners. They and all linear combinations are orthogonal to E1. When considering waves, n equals 2, so we have an n-1 or one unique orthopartner, as we saw. But now we have n equals 3 for radar and n equals 4 for general optical scattering. So we have 2 and 3-dimensional spaces for our null vector, respectively. So now we have not just a single orthogonal state, but a whole subspace of orthopartners. The set of unit vectors in this subspace, shown as W, is formed as a unitary weighted sum of basis vectors. For n equals 3, using just two angles, gamma and tau, as shown. Note, by the way, that this tau is not the wave ellipticity, and from now on, it represents a phase angle weight for combining the two Pauli vectors in this subspace. And we obtain a family, all members of which are orthogonal to K. This acts as a multi-dimensional switch for the pixel, in fact. So this is a new idea in polarimetry, orthogonality not just as a fixed partner state, but a whole set of partners, multi-dimensional orthogonality. So let's consider a familiar example to cement these ideas using polarization for mirror cancellation. Mirror reflection is, in its ideal sense, has a very simple S matrix, just the 2x2 identity, and so its Pauli vector is just the unit vector in the first Pauli dimension. And the orthospace is then spanned by unit vectors in the other two Pauli dimensions, 0, 1, 0 and 0, 0, 1. Now let's find the most general vector in this orthospace, which switches off mirror reflection. Here it is, W, a function of gamma and tau. And here is its equivalent S-matrix form. Let's call this family S unmirror or just sun mirror. The fact there is a whole family of S matrices for mirror cancellation is normally hidden by a very singular property of matrices like sun mirror. They all respond to circular polarization like a switch. Like-handed circular response is always on, i.e. it's never zero. This is because the singular vectors of matrices like this are always circular pole. So our orthostate diameter for this family always connects the north and south poles of the Poincaré sphere. Hence, if we transmit one sense of circular, it always comes back in the same sense. Reflection through the point I first takes us to the other pole, but then the 180 degree rotation brings us back to our starting point. Consequently, opposite sense circular switches all sun mirrors off, while mirror is turned on. This is often expressed as circular polarization provides mirror cancellation, but actually we see it now as a wide family of S matrices that can do this. The fact that there is a whole family of matrices that keep a pixel off is a powerful concept, and one we shall see that generalizes to any scatterer, not just a mirror. Although in general our families don't have a fixed set of singular vectors like this particularly simple one does. But first, let's look at an example of circular on-off mirror switching in radar using a burner machine operated by JAXA. Here we show an image from a satellite radar, ALOS-2, operated by JAXA. The x-axis is azimuth or cross range, and the y-axis is range, both in terms of pixel numbers. It shows a section of northwest coast of Scotland, so north is to the right. ALOS-2 is a burner machine. It provides the full calibrated S-matrix for each pixel. But here we simply use the matrix to generate the scattered power when we transmit circular and receive the opposite sense. This is mirror on territory. And the closest thing we have to a mirror is the ocean surface, where we can see clear wave patterns in the ocean. So, if you are an oceanographer, for example, then using mirror on states like this is good. But if, in contrast, you see the wave reflections as nothing more than clutter, unwanted background, and are interested in, say, ship detection, then switch the mirror off, like this. Here we simulate the case for like circular transmit and receive. Now the waves have gone, and we see some ships more clearly visible as bright points in the ocean. Note how land surfaces also change. Here we can see forests much more clearly than before, so foresters use like circular. Also note we have some azimuth ambiguities in this data. You can see the ghost of peninsulas against the low backscatter open ocean shifted in the x or azimuth direction. We will return to this example later, because although this demonstrates the potential for using orthogonality, it is by no means optimum. We can do better than this. We can do better than just using circular polarization. And to do better, we need to explore the landscape of this new orthospace. So given our new realization that there is a whole subspace of possible places to be in the null of a k-vector, where exactly is the best place to be? Are there any mountain tops in this space? To picture this, we can construct pairs of orthogonal vectors w and w perp as shown here in the orthospace using just two angles gamma and tau as shown. Then all possibilities can be represented as movements over a sphere where each base pair lie again in antipodal positions along a diameter. But remember, this is not the Poincaré sphere. For that sphere, each point P on the surface represents a two-element complex wave vector, whereas here each point P represents a three-dimensional W vector. Let's call it an orthosphere to avoid confusion, a sphere of orthogonal possibilities. The phase difference between components again is the tilt of a plane, and gamma, the amplitude ratio, tells us how far to go along a great circle. Just like the green way of locating points on the Poincaré sphere that we considered earlier. A sphere where each point represents a higher dimensional object. Now, for any chosen point on this sphere, we can ask how much power is in the component of W for any vector Ks. Ks would be a sample from a neighboring pixel, for example. The answer is just D, the magnitude squared of the Hermitian inner product between Ks and the chosen W. So as we move over the sphere, varying W for a fixed Ks, D will vary, and it will have peaks and valleys, and we want to stop on top of the tallest mountain, so to speak, the highest value. This then represents the maximum response for the pixel, and our best chance of detecting things, while still, of course, guaranteeing, as for all points on this sphere, they guarantee a null response for the reference. An example. First, we have to set up a problem. Let's insist again that mirror reflection is to be null, always. Then again, we can set up a family of W vectors as shown, functions of gamma and tau. And now, note that circular polarization is only a special case of this family. Now consider another general pixel, not the mirror. It will have a k-vector. Here is a numerical example just for illustration. There is no special significance to these numbers, just not a mirror. And here is the landscape, D, for all W vectors mapped over the orthosphere for k, with tau along the x-axis and gamma up the y-axis. We see a mountain with a peak in red, but not for like circular. We need a way, therefore, to find this peak automatically, given that it's not a simple state like circular pole. So just to be clear, we see that like circular is not the optimum place to be for mirror cancellation in general detection. Our approach has to be adaptive, just like VPA was in old ortho. It has to be adaptive to the local pixel k-vector under consideration. Now let's try and find the mountain peak for any given k and specified null vectors, a mathematical optimization problem. So here is the problem in algebraic form. We take any Pauli vector E1, not just a mirror, this is the most general form, and use it to find known vectors in the orthospace E2 and E3 as shown. Then generate a general vector in the subspace, W. But how to choose the two angles gamma and tau to find the top of the mountain for any given vector k? A problem in optimization which can be solved. The details are in this reference if you want to see them. And we just show the result. What you do is you project k onto the two vectors E2 and E3, then use these two complex numbers Z2 and Z3 to find the two optimum angles as shown. For example, tau is just the angle, the phase angle between those two complex numbers Z2 and Z3. This then takes us right to the top of the mountain, guaranteed, to a particular point on the orthosphere with coordinates tau and gamma. As k changes, this point, of course, will move over the surface of the sphere to stay always at the top of the mountain. And we have an adaptive optimization system. And this approach scales to higher dimensions, although with some modifications, and here I just give you a summary, a flavor of it. For example, for general scattering, not just backscatter, the Pauli vector is four-dimensional. So HV and VH are no longer equal, S is no longer symmetric. We might call this the optical canceller, as it applies to all optical monomatrix systems, as well as bistatic radar. Here again we can move directly to the top of the mountain using optimization. The change here is that we now have a three-dimensional orthospace for each pixel, lots more room to move around in. And so for a given reference E1 to be nulled, we have E2, E3 and E4 spanning the orthospace. The solution is obtained by first projecting, again, the sample k from another pixel onto the three known basis vectors of the orthospace, and then using these projections to calculate three angles this time to obtain the optimum weight vector w. So no more simple orthosphere geometry here, we've moved up a dimension. But for now, let's return to radar backscatter and the comfort of the orthosphere. It's time to wake the elephant and consider speckle again. So, just to summarize, in the past few slides we have shown how we can turn any pixel in an image off and still have a subspace of options for other pixels. For any given such pixel, we can also find its maximum response, subject to the null reference remaining unchanged. A kind of constrained optimization. But to make it all work, we need to have each pixel associated with a single k-vector, an S-matrix. Ironically, of course, that is exactly what a burner machine delivers, so we could apply these ortho ideas directly to one-look data at maximum resolution. If only. We have to worry about speckle. Sure, we can null any individual pixel, but due to speckle, those close neighbors, even though they may come from the same uniform background, will not be null and will show high variance fluctuations. So what to do? The general answer is to first speckle filter by summing a weighted average of local T matrices. This reduces speckle. The result, however, will be depolarization, a full rank T. So we then need a way to take an average T and estimate a dominant rank 1 approximation. Remember, depolarization does not completely destroy information, as Chandrasekhar showed. There are many ways to do this, perhaps using a physical model, but here we employ an eigenvalue approach. This provides, in a mathematical sense, the best guess S-matrix for any T by taking the maximum eigenvector and discard an eigenvalue and discarding the rest. So we start with rank 1 from the SAR processor, then average to generate depolarization and full rank. Then we return to rank 1 by eigenvector extraction. This then provides a rank 1 approximation to the whole image, every pixel, with speckle reduced. Just one last thing before we apply these ideas to some data. So far we have talked about nulling a pixel in the image, but sometimes we may want to null a cluster of pixels forming some segment of the image that we know is a connected region in some way. We can adapt this filtering scheme to deal with this case as follows: pixels or segments. So sometimes we want more than pixel nulling. Say the green or red segments shown here could be fields of different crops, and we wish to null their response as a group. To do this, we take all the speckle filtered rank 1 estimates for included pixels and form their new matrix tseg, having already, remember, discarded lambda 2 and lambda 3. So tseg is formed as an average of lambda 1s only. This matrix again will contain depolarization, but again we can find the best segment estimate of a single k-vector by a further eigenvalue analysis with new eigenvalues, let's call them mu. Now, however, we cannot obtain a perfect switch unless all the pixels, of course, are identical. The on-off ratio, in fact, will depend on the eigenvalue ratio of this tseg. In other words, the ability to switch off a segment depends, as it should, on the variance of rank 1 approximations across the segment. If the mu's are equal, then we cannot use orthogonality on this segment at all. There is too much intra-segment variation from our sensor, so perhaps we could change frequency, angle of incidence, or date, season of acquisition, and try again. So now we have all the tools we need for pixel or segment nulling using this orthogonal process. Now it's time to illustrate and show you some examples. So our examples are all from the JAXA sensor ALOS 2. This has a single frequency of operation, L-band, or around 30 centimeters wavelength, which is well matched to most land use applications. But questions about other frequencies we shall leave to the end, mainly via the provision of some free software, which I'll tell you about, to try this all out for yourself, on your own data, from your own sensor. So let's look a little bit at L-band ortho. So here's a summary of our processing scheme, just to remind you. First, we take SAR data and apply standard speckle filtering of choice to generate high-rank T imagery. Then we replace each pixel by its rank 1 T approximation. In that image we identify a pixel or segment of interest. This is the pixel or segment we wish to null. This also defines a pair of vectors E2 and E3 that span the orthospace. We can then process every other pixel in the image to find the maximum signal in this orthospace and form an image of D. We can repeat this process for as many pixels or segments of interest we require. As an example of the potentialist adaptive method, let's compare it to the simple circular pole mirror cancellation we discussed earlier. So here again we have a repeat of the co-circular SAR image from ALOS 2. This is mirror cancellation, and so you see the ocean surface is dark, very low reflection, and ships are clearly seen. Now let us apply the adaptive canceller using as a segment a patch of ocean surface. So the reference patch used, or segment, is shown top right as the white rectangle with the corresponding pair of null V vectors as shown, and these vectors are then applied to every pixel in the image in the optimization process. Notice how the ocean backscatter itself has been reduced much further even than circular. Note the scale on the right hand side is much lower than for circular. Note also that we have performed a Pauli cross-pole sum to help reduce azimuth ambiguities as well. The ships are still nicely visible, they are not cancelled as point targets, but now they have much better contrast against the background, allowing us much more dynamic range for detection of smaller craft, for example. Note also how the land surfaces have changed. Forest becomes visible, but the main influence is in changes in surface topography, exposing geological differences in the land. This area is rich in geological diversity, being part of a Scottish National Geopark region in the Northwest Highlands. Any sloped surface contrasts strongly with the reference flat ocean reference, and our optimizer emphasizes these differences. So this shows that the canceller has applications not just in oceanography, like ship or ice detection, for example, but in enhanced land use imagery as well. So let's investigate a more mixed site to explore the land opportunities a little more. So this scene again from the ALOS 2 database is centered on the city of Glasgow, in the center of the image there. The River Clyde can be seen running through the city, opening into the sea top right. And the large expanse of water just below it is the start of Loch Lomond. North again is off to the right. This is speckle filtered full rank T data and is the total backscatter, the sum of the eigenvalues. Our first task is to take each pixel and convert it to rank 1. This we do in the next slide, which shows the largest eigenvalue lambda 1 only. We see some loss of energy, particularly over the forests, but it could be argued this is just the depolarized noise-like power due to the speckle filter averaging. We see no loss of variation in backscatter and texture for different land use types. Information is still there. And the really key thing now is that we can turn any pixel here off and explore a whole space of possible polarization combinations for the other pixels. This we can use to enhance or suppress land use types. Let's take an example. Glasgow has open moorland with short, dense vegetation cover to the south and north of the city. By selecting a small segment in this moorland, we can see it is eliminated, the dark regions, to left and right of this image, at the same time as improving the contrast between open moorland and urban developments. If the relationship between these two land use types is of interest to you, then this kind of filtering can be more useful than trying it from the original full rank SAR data, for example. Also, if you look carefully on those dark moor regions to the left of the image, you can see an array of bright point scatterers. This is Whiteley, the UK's largest onshore wind farm facility, with over 200 large wind turbines located on high moorland close to Glasgow. And these are detected by the detector because of their different response, in polarization terms, to the background of the moorland. But perhaps you want to suppress urban scattering, in which case we can rerun the process. Just go back through, and now we can use a small segment in the city area to obtain a completely different SAR image from the same data. And here it is. Let's kill the city response. We see that urban suppression is less successful than the moorland. Some residual urban reflections remain. And this is because urban scattering, of course, is much more complex and more difficult to characterize by a single rank 1 system. To quantify this variation, we could use an urban mask to isolate urban pixels and then calculate the eigenvalues mu of tseg, as discussed earlier. Moving our attention now onto agricultural areas. This is March in Scotland, so many fields are fallow, but some have winter crops. We can select a field as a segment and change the image yet again to null the croplands. And here's the result. So yet again, an image with completely different contrasts. In it, we can see the network of fields, with moorlands now quite visible and the wind turbines again. This could be useful for those interested in the ratio between cropland and other land use types, and identification of boundaries between different types of vegetation cover. Finally, the most challenging perhaps, we can even turn off forests. This may seem surprising, as random forest canopies are strongly depolarizing structures, but remember we have removed that depolarized part through the rank 1 process, and so we can select a forest segment to assess our ability to remove forests from the image. And here we go. A pretty good job at forest removal, even outside the small test area used for null state calculation. This may be useful for applications like search and rescue in forested regions, for example, where we wish to suppress standard canopy response and see only anomalies, features that scatter polarized waves in a different way to the forest. So in conclusion, we have been on a journey of revisitation. Radar polarimetry started with orthogonality, then forgot about it, and now I propose we return. Not to say we abandon all the other good decomposition stuff, of course, just to consider it as an option for processing data. The key idea is that while orthogonality on the Poincaré sphere leads to a unique partner, as exploited even in the early days with techniques like VPA, in multidimensional systems of order n, like the Burnham machine where n equals 3, we can have n-1 dimensional subspace of orthogonal solutions. This gives us lots of opportunities to process images in different ways depending on application criteria. We have shown how to do one thing in orthospace, stand on top of the highest mountain. But what else can we do there? Well, for that, it's over to you. As mentioned earlier, it does seem a bit like throwing away data, but I hope, having seen the examples, you can see that it's possible to interpret that as discarded noise rather than throwing away data. And the benefit you get is nothing from something, the ideal switch. Now, if you want to try this out for yourself on your own data or your own sensor, there is some free software written by my collaborator on the project, Ashton Richardson, and available at this site. So in conclusion, let me just say, let's stop being so orthogonal about orthogonality in radar polarimetry and embrace it as a useful concept that may lead us to new and exciting applications of polarimetric radar.